All right, welcome back. Okay, so last time we did the BJT voltage divider bias circuit, and we learned how to solve that using the Thevenin solution, where we went ahead, took the front end, Thevenized that, and basically reduced it down to almost a base bias. Actually, it was a base bias version that we then could solve more easily. Now, this is another technique in order to solve the same circuit. This is applicable sometimes. Sometimes you can go ahead and apply this technique for solving these circuits. Now, as far as when you can solve this, a general rule of thumb over here is if you find that the value for R2, the resistance of R2, is less than 0.1 times beta times the resistance of that emitter resistor. So if this is true, then we can go ahead and consider IB, the base current, to be negligible. And if that's the case, then we can go ahead and we can say then that instead of IE being equal to IC plus IB, which still is very much true, we can then make the approximation that IC is about equal to IE, meaning that IB's contribution is very small. It's negligible. Now, so that's just kind of a rule of thumb. You don't have to memorize this on any type of exam that I give. I would actually tell you in the problem statement, use the approximation technique or use the Thevenin technique. Both of those pretty much cover your bases for all of these voltage divider bias circuits. Now, if we can go ahead and use the approximation technique, then we're really going to end up making life much simpler for solving these. Actually, a lot simpler. So let's go ahead and let's step through how to do that. Okay, now the first thing we want to do, if we're going to consider IB to be negligible, meaning, you know, it's pretty much almost zero, then we can just apply the voltage divider equation to this voltage divider that we have right here. So I'm going to go ahead and say that we are looking for V sub B. Okay, we want to know what the voltage at this point is. Okay, so we can go ahead and solve for that really easily using the voltage divider equation. I'll go ahead and write this off to the side here where I still, let's see, I'll put that right there. Okay, so VB is going to be equal to, well, it's the voltage on the input to the voltage divider, 24 volts, times R2, which R2 is 30K, divided by R1 plus R2, which is 130K plus 30K. Okay, what does that end up giving us? 4.5 volts. Okay, so essentially we just found out that the voltage at this point is 4.5 volts. All right, so that's the first thing you want to do. Pretty straightforward. Next up, we want to go ahead and figure out what the voltage at the emitter is. So we're actually looking for the voltage at this point, V sub E. Well, the nice thing here is we can go ahead and just say that 4.5 volts at this point minus the 0.7 volt drop, right? Because between the base and the emitter, we have this PN junction. We have a diode that's been formed. We have a 0.7 volt drop from VB to VE. So we can simply say VE is equal to VB minus 0.7 volts, or in our specific case, 4.5 volts minus 0.7 volts. And what does that end up being equal to? 3.8 volts. All right, so we figured out what V sub E is equal to, 3.8 volts. Okay, now where do we go from here? Remember, our goal is to find out the operating parameters, so we want to know the collector current, as well as the voltage between the collector and emitter. So from here, we can now figure out what I sub E is. Remember, I sub E is the current that's flowing through this emitter resistor. So we can find that out just by using these two values and applying Ohm's law, right? If we have 3.8 volts here, and we drop 3.8 volts, right? Because we have 0 down here, so 3.8 volts dropped across a 3K resistor, we can now say that I sub E and just apply Ohm's law. So I sub E is equal to 3.8 volts divided by 3K. Okay, that ends up being equal to 1.26 milliamps. All right, so I sub E we found to be 1.26 milliamps. Now remember, the approximation technique. We're saying IC is approximately equal to IE, and we just found IE. So now, I can go ahead and say IC, which is approximately equal to I sub E, is equal to 1.26 milliamps. Okay, so now that easily gets us to the collector current. The last thing we need to find is the voltage between the collector to the emitter, right? The voltage drop across our transistor here. So now we can go ahead and just do the same thing we've done before, just applying Kirchhoff's voltage law over here. So I'll draw it like that and say V sub CE. What is that equal to? Okay, so remember, we have 24 volts minus this voltage drop minus this voltage drop gives us this, right? We have to drop 24 volts across this whole thing. And so if we know the voltage drop across RC and we know the voltage drop across RE, we just subtract those two from the total applied 24 volts, and that value is VCE. So we can write that out as VCE is equal to 24 volts minus 1.26 milliamps times both of these resistances, right? I'm going to go ahead and just combine both of these resistances here. 8K plus 3K. Okay, so it's just Ohm's law, right? We have both of these resistors, the 8K and the 3K, so the total of 11K times our current that's flowing through it is the voltage drop across both of these. And if we subtract both of those from 24, we should get VCE. So VCE ends up being 10.06 volts. 10.06 volts. Okay, and that's it for the approximation technique. See, it's pretty easy to apply. Now, we'll go ahead and finish this up by doing the load line analysis on this. So let's go ahead and draw ourselves a load line. IC on the y-axis, VCE on the x-axis. Okay, and remember the two things we're interested in. We want to know this point, which occurs at cutoff. So we're interested in what VCE is at cutoff, and we're interested in what IC is at saturation. Okay, now let's go ahead and do cutoff first. So if we go back to the original problem here, for cutoff, if you imagine this is an open circuit here, so we have no current flowing through it. If we have no current flowing through it, we have no voltage drop across RC, and similarly, no voltage drop across RE. So that means between the collector and the emitter, we have 24 volts, right? Because this is behaving like it's open. Okay, so cutoff occurs here at 24 volts. Okay, now we need to go ahead and figure out what IC is at saturation. Let's go back over here. Now remember, for doing the load line analysis, we're going to take that saturation voltage to actually be 0. We're letting this transistor behave like a perfectly closed switch. Perfectly closed switch would just be a wire. So we have 0 volt drop between the collector and the emitter. Now, if that's the case, what is IC going to be at saturation if we have a 0 volt drop there? Well, it's just going to be 24 volts divided by this 8K plus the 3K, right? So if this was just a wire here, 8K plus 3K is these two resistors in series. Take 24 volts, divide it by that, and we're doing Ohm's law, and we'll get what the current is, what IC is at saturation. So over here, we're going to get 24 volts divided by 8K plus 3K. Now that's going to be equal to 2.2 milliamps. Okay, so now that we've established what occurs at saturation, what IC is at saturation, and we know that this is 24 volts at cutoff, we go ahead and draw this line. And now we need to go ahead and place our Q point on this. Now remember, we figured out what our operating parameters, essentially our Q point, is already from the approximation technique. 1.26 milliamps, and our VCE was 10.06 volts. Okay, I'll write those off on the side here. IC equals 1.26 milliamps, and VCE equals 10.06 volts. Okay, we'll check that out. IC 1.26, just a little above the halfway point. So maybe right about here. And notice that should be just a little less than halfway. So if the halfway point is 12 volts, should be a bit less than that. Well, it is. It's 10.06. So 1.26 milliamps here and 10.06 volts there. And here's our Q point. Okay. So essentially that finishes up this problem. Okay, now the whole point of doing all of that transistor analysis, we're really getting ready for using transistors as an amplifier. Like I said, there's two fundamental things that you're going to do with a transistor. One of them is treating it like a switch. It's either behaving as though it's saturated or it's in cutoff. But the other really big application of a transistor really is to amplify signals. We want to take something small, some small signal, maybe, millivolts of change, and make that larger. We want to make it, a volt or volts of change. Okay, so this is kind of the idea of amplification. We're just going to take a small changing signal and make it larger. Now, transistors already inherently do this, and hopefully at this point you've already kind of caught on to that, because of the whole idea. A small amount of base current produces a large amount of collector current, or a small amount of changing base current produces a large amount of changing collector current. So this is kind of what I'm setting up over here. Obviously, we're missing a lot of circuitry that's needed. We don't have a voltage that's applied. We don't have resistors, all of that stuff. But just over here, you can see that if we take a signal, and remember, you're going to have a positive and a ground, or some sort of common voltage between the two. Voltage is always between 2 points. So over here, our input signal would be applied to both of these terminals, right? And you'd have this changing signal here. And if we have a changing base current, we would have a changing collector current. So inherently, transistors already do this. Now, the most common type of transistor amplifier that you would see, and one that you would start off using, is what's referred to as a common emitter amplifier. Now, we call it a common emitter amplifier or common emitter mode because both the input and the output signal are sharing this same emitter. Or in other words, the emitter is common to both the input signal and the output signal. However, what this drawing is failing to demonstrate is that we would really prefer to work with voltages. So it'd be nice if our input and output was not just a current, but was a voltage. And then for that purpose, we're going to have to convert voltages to currents, since the transistor natively is amplifying current. Well, we just do that with a couple of resistors here. So what I'm showing over here is a changing base voltage, a changing input signal, if you will, which is causing the base current to increase and decrease, and that's causing the collector current similarly to increase and decrease. But notice our output in this version is really the voltage between the collector and the emitter. So our input voltage, VBB, is getting amplified by this transistor, and we're getting an output that changes, and that output is the voltage between the collector and the emitter. So let's kind of take a look over here. We're talking about amplification. Let's ask ourselves, well, what happens if my applied voltage, my input signal, what happens if my applied voltage changes? Specifically, what happens when it increases? Well, if it increases, what do you think IB is going to do? Remember, IB is just proportional to the applied voltage. It's by Ohm's law over here. So if VBB increases, IB will increase, right? And if IB increases, what does the linear model of our transistor tell us IC is going to do? IC will also increase, right? As IB goes up, so does IC. IC is equal to IB times beta. So they're proportional to each other. We expect IC to increase. Well, what happens to the voltage drop across the collector resistor if IC increases? Well, as you would expect by Ohm's law, the voltage drop across RC or VRC will also increase. Now, what happens if VRC increases? What's going to happen to VCE? Well, notice if my voltage drop across this resistor goes up, then that means my voltage between the collector and emitter must go down, right? Because this value is constant. We have KVL that we have to satisfy. So if I had 10 volts here, and this goes up to 5 volts, my remaining voltage here is 5 volts. If this goes up to 8, my remaining voltage here is 2. So when VRC increases because IC increased, then by KVL, VCE must decrease. Okay, so that's kind of the relationship I wanted to demonstrate here. As our applied voltage, as our applied signal goes up, our output signal actually goes down. Okay, now similarly, I'll go through this one a little more quickly. What happens if VBB decreases? Well, if VBB goes down, so does IB. Our base current goes down. If our base current goes down, what happens to IC? IC also goes down. Well, if IC also goes down, then the voltage drop across RC also goes down. And if VRC goes down, then by KVL, VCE must increase. Okay, so when our applied signal goes down, our output signal goes up. When our applied input signal goes up, our output signal goes down. So what that means for us is, if you think about VBB as a changing voltage applied to the input of a transistor circuit, as this goes up, VCE goes down. And as VBB goes down, VCE goes up. So we're actually getting inverted here, right? When this is high, this is low. When this is low, this is high, right? So our signal gets inverted as well as being amplified. Because remember, IB compared to IC, it has that relationship of beta, has that relationship of that gain. Okay, so we get a bigger signal for sure, but we also get it to be inverted. Okay? Now, as we apply amplification to a real transistor circuit, now all of a sudden the load line kind of starts to make sense why this is useful. Remember, we have IC over here, VCE over here. We're defined by these 2 points. What happens at saturation? What's VCE at cutoff? So notice here, if we were too close, remember our Q point. If we started out too close to cutoff, then we had all of this room for this Q point to slide up, right? As our input signal gets applied to the transistor, we have all this room for the Q point to slide up. However, it doesn't have much room to go down. So what ends up happening is we end up losing part of our signal. Our signal should And remember, we are inverted, so as we get closer to cutoff, it means we can't go as high for VCE. So our signal gets clipped over here. We should have done this. However, that's not what we get. We get this flat line because at this point, we just hit cutoff. This Q point, you can imagine that this Q point just slammed right into cutoff mode, and our transistor, it's just in cutoff. It can't do anything. It's just acting like an open switch. So this happens at cutoff if our Q point is too close to cutoff. And similarly, in the other direction, we also have another problem. If our Q point is too close to saturation, then we don't have enough room in this direction for our input signal. So what ends up happening is we end up clipping here at the bottom. Okay, so over here, this would be at saturation. Okay. Now, if you're trying to faithfully reproduce a signal, meaning, I want to keep the integrity of that signal, then this is bad news. If you're trying to make a guitar sound really cool, if you're trying to add that distortion, if you're trying to produce music, then this is actually really useful. This is really cool. So something to keep in mind, and also kind of showing now the usefulness of this load line, we really want to start out with our Q point being right in the center. If I go back to the previous problem, this gives me as much room in this direction as it does in this direction. If my Q point is pretty well in the center, right? So that's how we can kind of avoid distortion of our signals. Now, notice that this Q point starts off before a signal even changes, before we have a signal that's going up and down. Our transistor has to be biased in the center of this linear region, right? I should say, the cutoff area is not good for amplifying, nor is the saturation region good for amplifying. Saturation and cutoff are great if you're trying to make a switch, but they're terrible if you want to make an amplifier. So I have to, just by the nature of using transistor, I need to start it off at some point in the center. If you notice, that means I'm at something like 4.5 volts. So when we're constructing amplifiers using transistors, we have to live with that Q point being somewhere in the center. And that requires us having a voltage that's higher than 0 volts. So what that means is our signals don't or aren't centered at 0. We actually can't have this with a transistor amplifier, at least not yet. So we have to have our signal actually be floating up at some value or centered at some value. That value we actually refer to as the DC offset. So our signal is always comprised of these two components. We have the DC offset as well as our AC component. Our AC component is the changing voltage, whereas the DC offset is where we're starting from. So you can think of that DC offset as kind of being this value here. Where is it that we're starting at? which, as far as the load line concerned, puts us right in the middle of the linear region, right? Because this whole load line is representative of the linear region. Okay, now what this means for our signals is if we're working with an AC voltage source, remember our signal's going to be centered at 0 when we're looking at an AC voltage source, right? Half of the time this is positive, and the other half of the time this is positive. So we're actually moving around 0 volts. Well, that kind of creates a problem for our transistor circuit, right? Because our transistor circuit wants to be biased at that Q point that's in the center of the load line. So how do we put these two together? Well, what we're going to use is actually a capacitor to do this. So this is referred to as a bypass capacitor. Now, the cool thing about a capacitor is a capacitor will allow the AC signal to get through, meaning the changing voltage will be able to get out. But we're going to lose this DC offset going through a capacitor in series. Now, similarly, we can actually create a new DC offset by just having a voltage at this point. So as our AC signal goes up and down around this DC offset, this capacitor removes the DC offset, and then we end up adding our own over here. Okay, now why does a capacitor do this? Well, remember that a capacitor in the presence of AC behaves or gives opposition to AC. In fact, we call it capacitive reactance. And if I can get a better view here, the formula for capacitive reactance, X sub C. And reactance, this is just a fancy way of saying resistance to AC, is given by the formula 1 over 2 pi times F times C. Well, if you think about DC, DC is nothing more than a flat line. What's the frequency of DC? It's 0, right? Well, what happens to the capacitive reactance if the frequency is 0? If you just plug 0 into this formula, you're going to see that the capacitive reactance essentially goes to infinite. So that means infinite ohms, infinite resistance. Another word for infinite resistance, open switch, right? So this capacitor, as far as the DC is concerned, this DC offset voltage here is concerned, won't be able to get through. This cap will act like an open switch and not allow it to get through. However, what happens to the capacitive reactance if we're talking about AC, not DC? If we're just looking at AC, if we're looking at a changing voltage, now we're going to have to make a little bit of a jump here and just work off of the assumption that the frequency is sufficiently high that this happens. But let's just say that our frequency for right now, let's just say it was infinite. Well, if you plug infinite into the frequency of the equation for capacitive reactance, you're going to get that the capacitive reactance goes to 0. In other words, it behaves like a short. Okay, so AC cap acts like a short circuit. DC, cap acts like an open switch. So for AC, it'll let it get through. And that's exactly what's happening here. This cap is saying, nope, I'm going to act like an open switch to all of your DC, but all of your changing voltage, all of your AC, I'm going to let you through just fine because of that capacitive reactance. And, like I said before, once we remove that DC offset, we're actually free to bias the output of this capacitor to any voltage that we want. We don't have to use a voltage source here. We could use a voltage divider. Hint, hint, I'm foreshadowing into that voltage divider bias, right? You could use the voltage divider, or you could use a voltage source. And now you've established a new DC offset at wherever you want it. So that's what we're doing up here. Okay, so if we take our very simple base bias transistor circuit and we want to amplify a signal, take something small, make it larger, we're going to go ahead and first we're going to put it through this cap to strip out the DC offset. We're going to give it our own VC offset, VBB. This would be the bias voltage that's necessary to get our transistor into the center of that load line, into its linear range. And now we can go ahead and have this changing signal cause a changing output in our voltage between the collector and the emitter. And then similarly on the output from that the output voltage, our voltage between the collector and the emitter, we then have another cap which will then establish our DC offset to be 0 such that we're right in the center again. Okay, so this is where we're going with this. Now that being said, this circuit would work. It's not that practical of a circuit. There's much better ways to do it. So we're actually going to be analyzing another circuit in the next class. So just to give you an idea, next class, the full common emitter amplifier circuit looks kind of like, well, actually it looks just like this, right? We have an applied voltage, we have this capacitor to strip out the DC, we have our voltage divider bias to establish our transistor to operate and have its Q point in the center of that load line, and then we have this cap on the output. So we'll be looking at this circuit next time. I just wanted to cover the approximation technique and get a few of the details of amplification out of the way so that we can fully work and appreciate this circuit. All right, thank you so much, and take care, everyone.